Alright guys, now today we're going to take a look at properties of limits, how we can kind of change them algebraically, manipulate them, etc. However, first things first is we're going to take a look at our bell work. And so if you haven't already done it, make sure you guys pause it and do it. Otherwise, let's go ahead and follow along. Alright, so assuming you guys paused it and already did it, let's take a quick look here at what this should look like. Now, when we're doing a cubic, the first thing we want to do is multiply two of them together, and then the third one. If you remember the binomial expansion, the formula, you're more than welcome to use it, but my guess is most of you do not remember it. So, this is going to become the limit as x approaches 0 of, and what we're going to do is we're going to go 2 plus x squared, and then we'll multiply it by 2 plus x again. So 2 plus x squared is going to be 4 plus 4x plus x squared, like so. Then we're going to multiply it by, oh, excuse me, by 2 plus x. Then we're going to subtract 8. And then put the whole thing over x. Just a quick. And so then here now I'm going to expand the 2 by putting the 2 into absolutely everything there. So it's going to be the limit as x approaches 0 of 2 times 4, which is 8, plus 2 times 4x, or 8x, plus 2 times x squared, or 2x squared. Then I'm going to multiply the x into everything, so that's going to be plus 4x squared, and then plus x cubed. Then we subtract 8 and put the whole thing over x. Now hopefully at that point you can see here that the 8 and the negative 8 are going to cancel. And then we can combine the rest of those like terms. So now it'll be the limit as x approaches 0. And over here we've got, let's see here, let's put the x cubed first. Then we've got x squared and x squared here, so we can put those two together to give me 6x squared. Then we've got our x's here and here, which we'll put those together. So plus, not 8, sorry, that's 12x. And the whole thing's over x, so our next step here, because we need to get rid of that x on the bottom, so we're going to pull out a common factor of x on the top. That gives us x squared plus 6x plus 12. And that's helpful because now if the whole thing is over x, those two x's cancel. And so then remember our last step is always to actually plug in, well, first step and last step is to plug in what the limit is. So in this case here, we're going to get 0 squared plus 6 times 0 plus 12. All right, now the next one here, we can see that in this case there's actually no problems, and so the first thing we do always is to just plug it in, and in this case it's going to be defined everywhere, so we don't need to worry about doing any of the simplification. So this will just become e to the 3 cosine of pi times 3 over 3. Now remember, we don't have to write limit, because once we do the substitution, in this case putting 3 in, we can stop. Just like over here, once we plugged in the 0, we didn't have to write limit anymore. So we only have to write limit when we haven't actually taken the limit. At this point, we have. Alright, so this will be e cubed cosine of pi, because the two 3's are going to cancel. Now, using your unit circle, you should know that cosine of pi is negative 1. So this is like e3 times negative 1, e cubed, I should say. And I would not leave the negative at the end here. I always like to put it at the beginning because I find otherwise students tend to forget and think that it's e cubed minus 1, and it's not. It's negative e cubed. Alright, so now let's get into the properties of limits, and we've talked about this to a certain extent already. This is not the first time you've seen it, so it shouldn't be scary. So I'm going to write it out in kind of the long form to show us what this really means. Now, we've already done this, and this just means it's the limit of both of these added together. So it's the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Now, based on what was written up here, they tell us that the limit as x approaches a of f of x is L, and the limit as x approaches a of g of x is m. So the answer to this is literally just L plus m, or in other words, the answer to these two limits separately. Now likewise, when they're subtracted, it's exactly the same. So the limit as x approaches a of f of x minus the limit as x approaches a of g of x, or L minus m in this case. So the key that we want to remember here is sort of the way that all of this is working. And normally you don't need to write this expanded form. You could just go from here to the answer, but I'm writing it the long way to make sure we understand it this time. Now if we've got them divided, you guessed it, that is the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, or L over m in our particular case here. All right, now if we multiply them, it's just going to be these two things multiplied. So the limit as x approaches a of f of x, see some nice big brackets here, times the limit as x approaches a of g of x, or in our case, L times m. Now if we have a constant here, that's just going to be the constant times, forgot the equal sign there, this is going to be the constant times the limit as x approaches a of f of x, or in our case, c times L. So you'll notice that the constant doesn't have to be in the limit, it can just come out. We'll talk more about that here in number 7. First, number 6. This is exactly the same as just saying the limit as x approaches a of f of x, all to the power of p. Okay, where we take the entire thing. We already know that this stuff inside here is L, so this would be like L to the power of p. Now, like I said, we would talk about that constant again. If we take a limit as x approaches anything of a constant, well, that literally just is the constant, okay? Because if you think about what this is in terms of an equation, it's just a horizontal line. And a horizontal line, no matter where we are upon it, it's going to be equal to whatever the value of the horizontal line is. So, in this case, c, whatever c is. It's just a parameter. Alright, so next up here, we've got two different functions, f of x and g of x, and we're going to apply these properties. Now, as always, if the limit does not exist, we're going to state why. Now, thankfully for us right now, that's really just the left side doesn't equal the right side. Alright, so let's take a look at this one here. This is the limit as x approaches 2 only from the left side. So as we approach 2 here on f of x, only from the left, that's going to give us 3. Then when I approach 2 from the left side on g of x, that's going to give me 1 there. And so 3 plus 1 is really just 4. I'll switch up colors a little bit here to help us. So this one is going to be that constant times the limit as x approaches -1 of f of x. So if I find -1 here, that's right here. And from both sides, I'm approaching -6. Constant of 3. And on g of x, as I approach -1, that's this point right there, on both sides I'm approaching -1 there. So 2 times -6 is -12. -3 times -1 is +3. -12 plus 3 is -9. Awesome. All right, let's take a look at the next one here. Now we're doing them when they're subtracted. So the limit as x approaches -3 on f of x. In both cases here, we're getting to -2. And on g of x, oh, that's an asymptote. And this goes to -infinity and +infinity on the two sides. Therefore, that doesn't exist. Now, as soon as one of them doesn't exist, the whole thing does not exist. Okay? So we got to keep that in mind, is that like as soon as one of them doesn't, this whole limit is just not there. Now, oh, we missed a step. Why does that not exist? Because the left side does not equal the right side, right? Positive infinity on the left doesn't equal -infinity on the right. All right, next one here is x approaching 6. It's -2 to begin with. And then we're approaching 6 for f of x. So if I approach 6 here, from both the left and right, I'm approaching -4. And for g of x, as I approach +6, we can see that from the left and right here, I'm approaching 6. Then I work that out. Negative 2 times negative 4 is 8 over 6, which is really 4 over 3. All right, let's keep it going. Keep switching colors here to make it easy for us. Now this is going to be 2 times the limit as x approaches 4 of f of x times the limit as x approaches 4 of g of x. So it's 2 times. Let's go find the limit as x approaches 4 here. So as we approach positive 4 right here, from both the left and right side, I'm getting negative 3. And for g of x, as I approach 4, that's this little vertex here, and from both sides, I am approaching positive 4. So when I stick all that together, 2 times negative 3 is negative 6, times 4 is negative 24. All right. One last color here for the last one. So remember this one, when we have this, it's the limit as x approaches negative 2 of f of x, and then we square the entire thing. So whatever our answer is going to be, it's going to be squared. So f of x, as we approach negative 2, that's right there. From the left and right hand side, I'm getting negative 5. And then negative 5, it's the whole thing squared, so that would be 25. All right. So, if we look at this one here, now we're going to take our f of x function, and we're going to take that limit as h approaches 0 of this big thing. Guys, I'm going to star this for you. You need to know this. This is going to be very important going forward. That's why I've asked you to do this f of x plus h a few times, even in our last unit. All right? So let's go ahead and take a look at this. This is our limit as h approaches 0 of 2, and I replace the x plus with x plus h, minus 3, same thing, replace the x with x plus h, and then I subtract the entire function. Now I like to just immediately distribute that negative, so it would be like minus 2x squared minus negative 3x, or plus 3x, minus 4. Then I put the whole thing over h. So that's going to be the limit as h approaches 0. Now let's expand that. So that's 2x squared plus 2xh plus h squared. That's just me expanding the perfect square, which is the first term squared plus 2 times the middle term plus the last term squared. Then I'm going to expand the negative 3, so negative 3x minus 3h. And actually, before I even write this here, you can see that the positive 4 and negative 4 are going to cancel. So let's just get rid of them. And then minus 2x squared plus 3x all over h. Now I need to put this 2 into everything. And so that's the limit as h approaches 0 of 2x squared plus 4xh plus 2h squared minus 3x minus 3h minus 2x squared plus 3x. And once again, a bunch of stuff cancels. The 2x squareds cancel, positive 2 and negative 2. And then negative 3x and positive 3x, those will cancel as well. At this point now, I've got just a bunch of stuff with h's. So I'm going to go ahead and take out that common factor of an h like we did previously in questions like this. And that gives me 4x, because the h came out, plus 2h minus 3, and the whole thing's over h. That cancels out our h. Good, we got rid of the problem on the bottom, right? That was when if we tried to just plug this in, we're dividing by 0. So now we can plug in our 0, and so this ends up being 4x minus 3. Guys, this is super important. We're going to have to do this a lot, okay? Now, anytime we're doing this as h approaches 0, I want you to know, everything that doesn't have an h is going to cancel. So you can see here the 4, the 2x squared, and the negative 3x all canceled. Everything that's left will have an h in it so that you can pull it out and cancel it with the bottom. It will always work that way every single time. It's kind of the whole point, and we'll learn about that in our next unit as to why that is. All right, so then we've got some exponential functions here, and we're going to take a quick look at those and kind of see how well we sort of remember those. But generally, let's talk about them a bit. So y is equal to ab to the power of x, which you should recognize either from previous math classes or from biology or possibly from chemistry with half-life should recognize that formula. All right, now we've got 2 or 4 different ways that these functions kind of exist as well. Our normal like exponential growth, which is happening when b is greater than 1, looks like this. You probably did that with population growths of like 2, for instance. The other form of growth is going to look like this, okay? This one here happens when it's an exponential like decay that's then been reflected, okay? And then for our decays, we've got our normal decay, which would be this if b is just between 0 and 1. And then we've got our one that is normally a growth but then has been reflected, okay? And so it would look like this one for our decay. So it's that first one, like, to kind of match these up. This one here, when reflected, would look like that. And this one here, which is like our natural decay, when it's reflected, would look like a growth. So it just has to do with the fact that if they're reflected, okay? Now, let's take a look at this next equation. This is just like some background information to help us to figure out why these things look the way they do, okay? Now here, I mean, we can analyze this a whole bunch and figure out exactly where all this stuff is. That's really pre-calc, right? The 2/3 means it's decay. The -2 means that we moved it down 2 instead of being at 0. And this -1 means we moved it 1 over to the right. But honestly, none of that really is important right now, because what we're looking at is just the limit as x approaches negative infinity and infinity. So in other words, our end behaviors. As we go to negative infinity, as we go to the extreme left of this equation, as x kind of goes to the extreme left, we're going to increase here, and we're going to do it without bound. We're going to eventually get up to infinity as it keeps going. As we go to the extreme right, or the right end behavior, it's going to hit that asymptote. So in this case, it's going to hit -2. Okay? When I look at this next one, now we're looking at a growth one, and we're just going to do the same thing. As the limit, as x approaches negative infinity. So as we go to the extreme left here, we can see it's going to, whenever it's approaching an asymptote, it's going to hit that asymptote. So this is going to stop at -2. And if there is no asymptote, it kind of just expands without bounds. So in this case, that's going to go up to infinity as it keeps going up. Now, if we look at these next ones here, we've got the other form of growth here. And as we go to the extreme left, it's going to go left and down forever. So it's going to plunge down to negative infinity. On the right-hand side, it's approaching that asymptote, and so it's going to approach -1, the asymptote there. Next one here, we've got a decay again. As we go to the extreme left, oops, it shouldn't have crossed there, it's going to just approach that asymptote, which is at 2. And as we go to the extreme right, it's going to go bigger and down. So the y value is going to approach negative infinity. Okay? In order to determine our work here, what we want to realize is that as we go to negative infinity, we only really have 3 options. It can go to negative infinity, it can go to positive infinity, or it can go to a number, where that number is a horizontal asymptote. That's really our only 3 options when we're looking at our end behavior, because that's what this is. So if we want to know what's going on at the extreme ends of the functions, these are really our 3 options. That's it. Alright guys, that's it for that lesson. So you guys can go ahead and work on those practice problems, okay? And I will see you next time.